Hi everyone, welcome to my presentation. My name is Sungjoon Choi and today I'll introduce our work on robust learning titled Task Agnostic Robust Learning on Corrupt Outputs by Correlation Guided Mixture Density Networks. This work has been done in Kako Brain with Sanghoon Hong, Kyungjae Lee, and Sungbin Lim. We are all living in this era of machine learning where collecting a sufficient number of data becomes more important than ever. For example, if you want to make a three-class classifier of a dog, cat, and cow, you'll probably start your training process by collecting images of dog, cat, and cow from web crawling or crowdsourcing. However, as we are all human, we make mistakes, such as labeling a sea lion as a dog, a camel as a cat, and a pig as a cow. In this paper, we assume that the training data contains some miscollected ones and present a robust learning method that could handle such errors in a dataset. As our title task agnostic indicates, our proposed method can be applied to both classification and regression problems. Suppose we are focusing on cat and dog classification. The ground truth target distribution let us collect a clean dataset. However, if our dataset is collecting from multiple sources mixed with on-target and other noise distributions, we end up getting a noisy dataset. In practice, we can always guarantee that our trained data are all clean and perfect, but it is rather more natural to assume that there exists some inconsistencies in a dataset, making a robust learning problem more important. There has been a long line of work in robust learning statistics where we assume that the data distribution is composed of a mixture of target and noise distributions. This model is called the Huber's Epsilon contamination model, and Huber and Sloan presented an optimal law given some knowledge about the contamination level. Usually it is assumed that the noise distribution is in the class of all probable distributions, which are independent from target distribution. Unlike the Huber Epsilon contamination model, we assume that there exists correlation between the target and noise distributions. And of course, this correlation is also a learnable parameter, and we would like to note that this correlation can be zero, and in this case, the target and noise distribution becomes independent under the Gaussian assumptions which generalize the Huber Epsilon contamination model. If we look back to our previous cat and dog classification task, now we assume that there exists some correlation between target and each noise distribution. In this paper, we present ChoiceNet that enables modeling and correlated outputs in a neural network in a fully differentiable manner. Similar to Bayesian neural network, we maintain the probability distribution over weights, but also leverage mixture distribution to handle inconsistencies in a dataset. Similar to Bayesian network, suppose that we maintain the distribution over weights of a target neural network. Since W star is a random variable, the resulting Y also becomes a random variable. Then, suppose we have another neural network whose weights are correlated with the target weight W star, the target weights. Then it is straightforward to show that the output of two networks, Y and Y tilde, are also row correlated. In fact, this is exactly what we wanted to achieve, modeling correlation between two outputs. However, we need to find a way to construct a row correlated W tilde from W star. The cornerstone of this paper is Cholesky Transform that enables us to define and sample correlated weights from the target weight statistics in a differentiable manner using a reparametrization trick. Furthermore, we can also leverage any network, for example CNN or RNN, as base network for feature extraction purposes. Finally, we leverage a mixture distribution to better model the noise distribution, where the first mixture k=1 is always dedicated for the target distribution. Now we have all the components to model the output with correlated conditional distributions. The resulting mixture of correlated density networks are referred to as ChoiceNet. An intuitive way to understanding how ChoiceNet works is that while the first mixture is in charge of modeling the target distribution, the rest of k-1 mixtures effectively divide up the remaining noise distributions. We have shown this in synthetic experiments, so please refer to this in our paper. These are the loss functions of both regression and classification problems. Also, for more detail, please refer to our paper. We conduct classification experiments on image datasets where we show that our method shows comparable or superior classification performance compared to the standard method under heavy noises. These are the other classification results: MNIST, Fashion MNIST, SVHN, Cypher10, and Cypher100. There are also more results on this paper, including sentimental analysis and imitation learning. To sum up, the ChoiceNet is presented that could robustly learn the target distribution given noisy trained data in both classification and regression problems. The cornerstone of our method is a Cholesky Transform that enables the mixture of correlated density network block. It simultaneously estimates the underlying target distribution and the quality of its data, where the quality is defined by the correlation between the target and the data generating distributions. So thank you for listening. If you have any questions, feel free to contact me via the following address. Thank you.